I'm live. I'm live. I'm live. We are live. We are live. I'm live. You're not live. I'm live. Right. I'm live. I'm live. I'm live. We are live. Okay. So, let me go ahead and organize this. Love how it disappeared. I dragged it over to my oh, there it is. It is just appeared. Okay. I don't know what happened. It just vanished into thin air for a second. What's that keybind? What's it? Super J. Super Control D. Super K. None of these are doing anything. I remember there was some key I could press. Dude, I think if I press when Super Shift M, like my computer shuts down, so I probably won't be pressing that presently. What is it? Let's go to my hyperconf file. sorry, don't worry about that. Let's go to my hyperconf file. Config. Hyper. Yeah, Nano, I know I'm a soy. I'm a soy using Nano instead of M. Or V. Dude, that one video of a guy coding an entire driver for the Linux kernel in V with no syntax highlighting. That is unique. There's one of that guy. Okay, which one? Yeah. Shift S. What is the key that makes me... I don't know. I guess we'll never know. I guess we'll never know. Okay, what are we doing today? Today, we are working on the orchestration computer for the Nether Star. So, as you know, Nether Star, it's my project, 30 million blocks to the world order, blah, 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 through the Nether terrain. We know this already. I'm going to be building a simulation. So, there's a lot of complex systems, and I thought, what if I made a 2D simulation where everything could go perfectly well, so that we could stress test the flight computer. Or, sorry, not the flight computer, the navigation computer, without the stress of the flight computer. So that's what we're doing today. We're making an interactive 2D simulation. It's not going to be especially difficult. I don't think there's really going to be collision, but it's going to be pretty simple. Let's get started. So we are going to cd to /run media grand sugar auxiliary m.2 dev. We're going to do cargo new. We're using Rust, right? Because I'm an Omega Chad. We're going to be doing. Let's do 2D. Nav sim demo. Cannot start. Nav sim demo 2D. There we go. Alright, and we are going to open this in VS Code. And we are going to start and get to work. But before we do that, I'm going to show you the other two projects that, or I'm actually going to show you how everything works and what I currently have built. Because this is, I'm not going into this blind. Hold on. Yeah. I do actually have a few prototypes that I've made of two systems, but I'm going to show you what is the navigation stack need. So we're not going to worry about communication. The orchestration system needs to navigate and communicate. But we are only, for this purpose, for right now, we're only going to worry about navigation, right? Because we don't need to worry about communication because we're not doing the flight computer stuff. It's all in sim. So we have the navigation computer. The navigation program would be a better term. And the navigation program has a responsibility. It needs to generate navigation data, right? It needs to generate waypoints. We're not going to worry about where this comes from, but all you need to know for now is that for some mysterious source, which if you really want to know is the data from the communication stack, it's going to send data in to the navigation computer about the LiDAR waypoints. So the LiDAR waypoints, or LiDAR points would be better, not waypoints. LiDAR point. It's going to be giving it to the navigation program. And so we have a few problems we need to solve. First off, we need to define what algorithm we're actually using. So the main algorithm that's doing everything is called RT star, or Rapidly Exploring Random Trees star. And what does this mean? So rapidly exploring random trees. Basically, we're going to talk more about this when we get into it. We're probably not going to get in this stream. This stream is mainly just going to be making the simulation itself. But what RT star fundamentally is you have a point on a tree of a path tree. That's where the trees comes from. You very quickly select a random point around you. That's rapidly exploring random. And then if there is a clear path, which you need some sort of collision information to determine if there's a clear path, you connect those points, and then that's a branch of the tree, and then you keep going until whatever. And you can put, the way you get it to go where you want is you put biases on the random factor, so it's more biased to go in one direction. So it's not random, it's pseudo-random, and you can just change the bias to do whatever you want. And this is what it's great about an algorithm like this. It's super simple to do that. You just change a number, you just add a number, and then it auto-magically, mathematically likes to prefer whatever you said. But there is two fundamental issues. Sorry, this is Rapidly Exploring Random Trees star, meaning it doesn't just create the tree, like I said, it also actively rewires itself. It can reconstruct its own tree to find an optimal path. And this is very computationally expensive, which is one of the reasons we chose Rust. But it also means that we need to try our best to reduce the amount of overhead as physically possible. And to do that, we need to take into account two pieces of information. The Rapidly Exploring Random Tree star needs to very quickly do what's called a nearest neighbor search. You have a point, and you need to find another point in some sort of data set that is closest to it. This is, like I said, it creates a random point around it, and then it finds the nearest point of the tree and tries to connect them. So we need to do a way to do a very fast nearest neighbor search. And to do that, we are going to be using a data structure, which is basically just a way of storing data, called a KD tree. KD stands for K dimension, so to be more specific, this would be K dimension tree. I'm not going to be talking too much about what this is currently, but I'm going to be talking more about this in the video. A K dimension tree is a binary search tree. If you've ever heard of a binary search tree, it's a binary search tree, except for instead of having one value, it can have K values. And it does it by alternating and doing some geometry math stuff. And I have a working implementation of a 3D one, but we're going to modify it to 2D. I do just want to make sure real quick that I am not privately live again. What value? I don't want that shit to happen to me again. Public. It is public. So this is the world can see this, all right? And so this is responsible for storing the nodes of the RT star tree. So this is responsible for housing the nodes of the R tree star. Or sorry, I should be more precise. A reference to the nodes of the RT star tree. The KD junction tree isn't actually storing the data of the RT star tree. The RT star tree stores its own tree in its own data structure. And what happens is the K dimension tree simply has almost like a surrogate, right? Like a reference to it. So if you need to find something, you search the K dimension tree, you find it, and then that points to a place inside of the RRT tree. So that's how that works. And this is by the way, when it comes to indexing, because we're using Rust and because one of the rules for this project is no recursion, the K dimension tree is iterative, not recursive, meaning there is no chance of a stack overflow. Basically, that's just memory safety. And then we're going to have another data structure that is responsible for holding another piece of information. We are going to be having, yet again, an iterative, but this time a quad tree. Octree in 3D. A quad tree is responsible, or we're talking more about what it is in a second, but it is responsible for holding the LiDAR point data. Why? And what is a quad tree? A quad tree, this one's a bit easier to explain, so I might actually just show you. Wow, flashbang. Imagine you have a bunch of data, right? A bunch of, let me make a bunch of points. And there's obviously going to be thousands more, but we want to real quickly generate a collision map based off of this, storing for each individual voxel of Minecraft. That would be incredibly expensive. So we instead have something called an octatree for Minecraft because it's 3D. But for our example, everything is in 2D. So you can imagine, imagine these dots are blocks. We have a quad tree. So instead of storing data where we don't need it, which is over, like instead of having this split up into a bunch of nodes, right? Like a grid where we have to search through it, that would be expensive. And the reason that would be expensive is because searching through an array, that takes time because you're continuously checking each element of the array to see if you find what you're looking for. Instead, a quad tree, we can store all the information that we need. So if we have nodes in here, we split up this section of the tree, and then we split up this section of the tree, just like this. So we split up the tree, or the grid, or it's, I guess you could kind of say it's both, until we have a representation of the data, but we don't waste empty space. Like there's a huge amount of space over here that's just, the computer doesn't really have to worry about it. And this also really neatly lets us represent specifically the type of data we're trying to represent, which is collision data. Because if we have nodes over here and we're just trying to determine a place to avoid, all we have to do is search the tree, and the deeper the depth, the more recursed it is, the closer you are to something that can collide. So it doesn't just tell you, is there something that you can collide with there? It's also sort of telling you the proximity to something that you could collide with. So it's giving us a distance measurement without any Euclidean math, and a super quick measurement to see, are we actually going to collide into something? So a quad tree is a really good fit for collision data in this particular, especially in this particular circumstance. And that quad tree is not here, but I do have it implemented. I'll show you that in a second. But that's going to be holding the LiDAR point data. An octatree is going to be the variation of that, where instead of there being a square and you divide it like this, you have, of course, another dimension, right? So you have to split it into eighths instead of fourths, because a cube, imagine splitting a cube, you have to split that into 8 smaller cubes, and then you keep doing that. So that's fundamentally how the algorithm. So we're not worrying too much today. Rapidly exploring random trees isn't our focus, right? This isn't our focus. Our main focus today is probably going to be these, though probably not. For the simulation, the simulation is what we're making today. And so what do we have to worry about for the simulation? The simulation is going to be rendered in something called Raylib. Raylib is a very simple, pretty much like a graphics API that lets you very quickly draw shapes and stuff. It's incredibly simple. It doesn't have collision or anything. We still need to do all the work. We need to implement mock craft. Basically pretend craft, because we still need craft. And those mock craft in today's example is just going to be the nav drone. Though by the end we are going to have a full representation of every craft in the navigation in the entire fleet. That's going to be the nav drone. So we have to implement LiDAR scanning, which means we have to implement raycasting. But to do that, we also need something to scan. So we are also going to be implementing cave generation on a voxel grid. So we are basically recreating Minecraft in 2D. A cave generation on a voxel grid. What does this mean? Basically, we are going to be doing a simplified example where instead of having a full nether generator, that would be incredibly expensive, and if I had another generator, I wouldn't need to do this in the first place because I'd already know where every single block is, and then I could just pre-compute the whole path ahead of time. Which, fun fact, if you watch the original streams where I went to the world border in the overworld, that was my plan. But that seemed impractical, I say, as I'm doing this shit. And so to do this, we just need to make a voxel grid. So we want to be able to do this. So this is the whole plan. If we go ahead and grab these points over here. Hold on. Whoops. I don't want to grab these. This is the plan for the navigation computer. This is what we're doing today. So we're doing this down here today. Alright. Why is it so hot in my room all the time? Like, I could turn my AC on right now, but it would just get so loud on the microphone. And I want to keep the noise suppression off so y'all can hear my keyboard clicks, because, I don't know, they're satisfying, I think. So this is what we're doing today. First thing I have to do is just get started, right? So here we are. Let's go ahead and just create a window, right? So I'm gonna do cargo add raylib. It's gonna add a raylib to the repository. Dude, I love cargo. I'm also gonna add preemptively rand because we're gonna need rand for the Perlin noise for the cave generation later. And let's just do RL handle and thread, I believe is what it exposes, equals raylib : and don't we need to use raylib : prelude : star, and that's going to equal raylib : raylib handle. Is this correct? Or init? What does this return? Respiratory for choosing window options before initially. Go to raylib builder. What does it take in? Okay, hold on, maybe I'm thinking of something. Raylib builder? Is this it? Okay, we do init. Okay, dot. Alright, so let's do, what size do we want it to be? We want it to be, because this is really for me, I think it will be fair to just do 25 dot size is going to be 2560 by 1440. But I think it would be interesting if we could preemptively make it dynamic as scale rather than size. I think that's going to be a good system to implement. And what else? I think that's pretty much it. So we can just do .build. Okay. And we should probably make this mutable. And then we'll just do a loop, or we'll do while rl handle. What's your problem? Mute must be attached to each variable binding. I guess that's fair. While rl handle dot is window ready, or probably not rl handle that should window should close, right? Then we should do let draw equal rl handle dot start begin drawing. We want the thread. Then we'll do draw circle. We'll do 0 0 radius. I'll do 200 and color. We'll do red. Okay, what's your problem? Oh, you want to be a float. Draw. Do you need to be mutable? Okay, I got a warning. What's my warning? You don't need to be mutable. Alright. Now if you go ahead and do cargo run, beautiful. So we have a basic window. Now I'm pretty much going to move all of this to a separate class called the renderer. So I want what should I call it? Like systems, I guess. Renderer.rs. And do I have to do it in main, or can I do it in like another file? Include.rs, can I do that? And then do pubmod include use render, or hold on, let's go here, don't save, hold on, delete systems. I'm still a bit new to Rust. We'll do mod.rs, I think it is. We're gonna do pubmod renderer. In the main, we want to do pubmod systems. Module should have snake case name. Okay. Okay. Renderer. Install code. Well, I don't want C++ debugging. JS language. So we need to create a structure called renderer. And the structure shouldn't need. Does it need to store the bodies that it needs to render? No, we push it to every frame. Okay, so public. Now, okay, so we'll just keep that blank for now. I don't know. Oh, yeah, you should know that. We'll do public, or do implement renderer, and we want to do public. Do we want to be able to instantiate it as a self? I mean, yeah. So let's do public render, and we want every time we do this, we want a pointer to we want to know what bodies it wants us to render. So we'll store the bodies to render in here, but we need to define that. So we'll go ahead and do objects, and in here we'll call body.rs and mod.rs as well. And this will say pubmod, or yeah, body. And then we'll go to, we'll save you, then we'll go to main, then we'll do pubmod body. or objects, and so you include body. Okay, so body is going to be a structure that contains body. No, yeah, we'll do render. We'll do render body. I think would be a better name. So we'll do public struct render body. What's your problem? File not found. Okay, well, your render body. This needs to contain. What information do we need to know to render something? Well, for our case, everything is going to be rectangles, but we need to. Not everything is drawn as rectangles as the end of the day, but that is, well, fundamentally not really their problem. So because everything's voxelized, we can get away with it by drawing everything as rectangles, but how we render it isn't really the problem. Yeah, it isn't really the problem of this. So yeah. But we first need to define some basic math stuff. So I'll make lib. This will contain some library information. Mainly for our case, we'll do vector.rs mod pub mod vector. Then we'll go to main pub mod vector pub mod lib. File declaration of lib is the target root of this creates library directory. To refer to it from other targets, use the library path. Name is the path. Oh, special function name. Okay. Library. Let's just call it library. All right. And for that, we need to create a vector. So public struct, we are going to make everything vector 2 because this is 2 dimensions, and they're going to store x in y data. Does this need to be floating? I want to say yes. Let's implement vector 2 for now and just say pub function new x32 y f32. That's going to return self, and self is going to be equal to x is equal to x and y is equal to y. Perfect. Okay, and we need to make u public. Now if you got a render body is going to need a position. So position to render it is going to be in, I think, scale space is what I'll call it. It's going to be equal to vec2. What else do we need to store? We need to store the rectangles. So we need to store a vector of rectangles, and it's going to be owned by this. So we'll create objects, new file, shapes.rs, go to here, mod, pub mod shapes, and shapes will do pub struct rectangle. This is going to contain data for a rectangle. We need the center point, center pos. This is going to be a vector 2 in what's it? Scale space. We need the size as a vector 2, and we need the rotation. This is going to be as an f32 in pi radians. And we can convert this to, okay, these all public. So a rectangle, we can just create it like that. So render body, it's going to contain a vector of rectangles. Or we could just call them rec. Or let's just call it a rect. I think that would be better. That's more concise. It's sort of the style of Rust is to make things short like that. Make these both public. And for this, we need to make you camel case. So we have the position and we have the rectangles, and each of them has a rotation from the body. That's fine, but we also need to have a rotation for the entire body itself. So we need to store the rotation of the entire body. Okay, so how do we need to define in renderer a vector of bodies, right? Or should we have one vector total and just get a reference to the, like we have the entity vector, and we just pass into the render function indices to that one giant vector that contains all the entities? Or do we store that vector in the renderer so that we don't have to we don't have to every frame give a reference? We can just push it. So okay, how about this? We push it to the renderer when we first start. The renderer can go through it. It continuously has a reference to it. But when we want to get rid of it, we call a free function. The free function will set its position in the vector to none and add that to a free list. So we don't have to continuously be feeding it stuff. We can just, and when we do add, it returns the index of it. It's not a tree, so we don't have to worry about anything like that. Okay, let's do that then. So we'll do bodies is going to be equal to a vector of render bodies so returning a vector of render bodies. That this basically tells the computer, I have this data for you and I want you to render it like this. Right. Actually, we don't. We haven't told it how to work with it. So the render function should be a pure consumer. It shouldn't take anything. So we should expose add render body, or push body would be better. And we want to have the body be a render body. And in return, we're going to get a usize, or an option usize. Option because it might not be successful. So to push a body, we need to also have a free list. This is going to be a vector of positions. So the free list contains a vector of indexes for this body. Or would it be better to do a hash set? Okay, so we're going to have the free list be a hash set. I believe that might be better. A render bot of use sizes. Make this hash set. Hash is like a hash set macro. No, okay, we'll just use hash set column now. And so what we need to do is we're gonna use something called if let. So we do if let, I believe sum, or sum, and we want the index equals free list, or sorry, we need a mutable reference to self for this. Free list dot, what is it, pop? What is it? We need to dot, what is it to take? I'm dumb, what is it? Is it literally just, is it get? What does this do? Gets it by value. No, I don't want to get it by value. I just want the most recent. What does take do? No, I don't want to take it by value. I just, give me your most recent one. What is the equivalent? Is it dot take? Set.iter.next, I guess. .ni C++ std library. I'm sorry, that was evil. I shouldn't have said that. So if that index does exist, it contains a use size for us, and we want iter. What is it? We want to own the data. We don't just want to, we want to consume it. So iter, what does into iter mean? Because consuming iter, right? That's exactly what we want. Dot next. So what this does is, because the index is now a use size and reference to use size, this means that ownership is being transferred to us. We're actively consuming the data, which is fine because we want to discard it after so nothing else can take the index. So if we got an index from the free list, we can just do self.bodies index equals body. And we can return the index. What's your problem? If maybe missing an else clause. Shut up. I don't like the if-else stuff in Rust. Like, come on, bro. I mean, it's not that big of a deal. It's easy to ignore, but still, it's annoying. So now we have to, otherwise, just say let index equal self.bodies.length, and we are going to push it. So it'll self.bodies.push body, and then we'll return the index. Cannot move out of self, which is behind a mutable reference, which does not implement the copy trait. So we want to we want to take the data, but we don't want to copy the whole set each time. I think we're just going to use a vector. I'm honestly not even sure if using a hash set is a good idea here. Maybe it is. I don't know, I'm not that experienced with hash sets, but I think we're just going to use a vector because it's not going to be like a million objects on screen at the same time, so it's probably fine. And so instead we could just do self.pop, and this will give us ownership. We don't need to include hash set. So basically, to explain what's happening if you don't understand, if we check the free list first to see if it has any indices available, it's basically saying, hey, or what happens is we have a vector of objects we can render, but occasionally we want to throw one out. Like, for example, if when it goes off screen, we don't want to render anymore. We literally remove its index, right? Or we just make it inactive, right? So it's still there, but it can't do anything. And when we set that index up as free. And so what can happen is if another body wants to come in, we first check the free list. This is to avoid memory issues. So we try to push it in where another body left off, else we will push it at the end of the vector. But this helps with memory efficiency. This helps with cache, because if we keep it as one contiguous block instead of having random holes everywhere, then the cache will be able to better predict. So it's going to be good for the CPU cache. But to do that, I'm now realizing this can't be a vector of render bodies unless we implement some other value in render body. We want it to be a value of option render bodies. So this means it might be a render body. So we just want to pass in some here saying that it does exist. Then we can go ahead and do a function. We can suppose another function. What could it be, like destroy body? And we need the body index as a usize, and this will return result. Were we successful? So it's either going to return nothing, or do we really want an error here? If we can't destroy body of the render set, it's probably because it doesn't exist in there. Is there any other possible case scenario? I guess technically there is, but all the other case scenarios would be catastrophic and we'd have to cause a program crash. So I think option would be better here, just saying was it successful. So we just want to return option nothing. So option null, just saying like was it successful, you know. So we will do if let self dot if let some node or some node used to trees some body equals self dot bodies dot get. Do you want it to be mutable? We just want to determine if there's something there. So we'll do get because it doesn't actually matter. So we'll just let get else, basically if we can't get the body, or you know it'd be even better because we don't actually need the body. We could just say if self dot bodies dot body index dot is none. Then it's not there, we will return none. Missing an else clause. Oh yeah, we want to return none. So we know there is a body actually at that position. So we're just going to go ahead and destroy it. To destroy it, we are just going to say self.bodies at that index is equal to none. We're not deleting it. Notice we're not deleting it, because if we did, that would push the whole vector. That would be catastrophic. That would be bad for time complexity too. So instead, we're just removing it. So it's no longer contiguous. It's just an empty space. And then we'll do self.freelist.push body index. And then we'll go ahead and return OK. What's wrong? Mismatch types. Found enum. Sum. So basically, to destroy the body, we're checking, does the body even exist? If it doesn't exist, then we can't destroy it because it doesn't exist. And if it does, we remove it from, we set its value in the vector to none. We go ahead and push that index onto the free list, and there we go. So now we have the free list set up. We can push bodies to the list and we can destroy them. To render them, we have to go through each body. We have to check, does it exist? If it does exist, we have to figure out how to render it, right? So we'll worry about that other one in a second. But for now, let's loop over it. So we'll do for body and self dot. Hold on, I think I actually don't need a mutable reference to self here. Dot bodies. So we're getting option render body. This will give us ownership. We don't want that. We want iter. This gives us a reference, which is what we want. And we can do this. We could say let body option. We could say let body reference, or let body, oh, just body equals body option dot. There was a command that lets you flip these as reference. Yeah, so it basically flips these. And if, yeah, and so we want to check dot unwrap or if it doesn't exist, we just, what do we want to do? It contains some value. Computes it from some closure. Okay, do we need to pass in anything? This is how you make a closure, right? So we can return the render body. All I want to do is, if it doesn't exist, I want to continue. So let's just do this. We'll do if body dot is none, then just continue, right? Because then it's just a contiguous, it's just a contiguous violation. Right? Then after this, body, it must exist. It literally cannot not exist. So we could say body dot expect, and we could say paradoxically body doesn't exist after check. I'm certain that this should exist. So this is, the body is still, yeah, it's still that. So we want to say body equals body dot expect. So we'll say let body equal let mutable. Do we, no, not mutable, because we can't mutate a reference. So there we go. This is shadowing, by the way, if you're wondering what this is. And, you know, there's actually a much better way to do this. We say if some body equals self.bodies dot, or some body equals body option dot as reference. So the else, so we can then say if it doesn't exist, then just continue. Else, we now have the body. So that's a much better way of doing it. The if let syntax, the let else syntax, it looks a bit strange, but it's not too difficult once you understand it. Now we need to render the body. To do that, we need to determine It's rectangles. So like I said, everything's going to be rectangles. So we need to figure out a way to draw rectangles. So let's do self.render body, and we're going to pass in the body. So reference to body. So we'll do public, or do not public, render body, and it's going to take in a immutable reference to self, and it's going to be taking in a body, which is going to be an immutable reference to a render body. And we need to output the success of it. Were we successfully able to render it? So we'll do that. Is there multiple reasons why rendering a body could fail? Yes. So is it theoretically possible for it to fail? Should it ever fail? No. There should never be a case where the body can't render. There should never be a planned case. If it fails, then we have to do a program crash. So I think it actually makes sense to not return here. So we first have to go through all of the rectangles and draw them. So we do have to do for rect in body dot rectangles, and again we want a dot iter so that we get immutable reference, and we want to render it. So how do we render the rectangle? Well, let's see. We also need the draw handle. It's going to be raylib. What type is it? Raylib draw handle with a lifetime. And then we want to pass that into render body as well. Use the move value. Oh yeah, this needs to be a reference. So what options do we have available? Okay, what does this do? Something, I bet. Doesn't tell me. Expected raylib thread. Function, okay, just tell me nothing at all. What is this? Draw triangle. How do I rotate it? Oh, look at this. That's actually useful. We have to do transformations, aren't we? Okay, this is going to be so much fun. So it's literally, well, I think it's these vectors. Are they? Oh, I think they literally are. I think these vectors are literally the vectors into vector 2. Wait, there's a vector 2 already existing? Oh, okay, there already is a vector 2, so we don't need our version of the vector 2, I guess. So I'll go ahead and delete the vector class. Fix everything that just broke. Shapes, you don't use vector 2, you use vector 2 from raylib. You don't use that. So we need to give it 3 positions, and to do that we need to define how do we rotate. We move it. What's that? We sign it. We have to like do, because like we have the shape, we have to rotate it around a point. So we need to, I think that's sign. (2D rotation formula). Oh, I was right. Yes. So, yeah. We now have to define our coordinate system. So it starts at the top left up here. And it goes down. This is Raylib's coordinate system. I think that's fine. I mean, I'm not a big fan, but it could be worse. Okay, so we have the vectors, but we need to convert them to the space that we're working with. I want it to be scale based. I want it to, if you divide it by 2560, what could you do to always get the same number? Or to like, if I have 1, what is the formula? Percent. So it's desired pixel size over screen size. So we have the vectors divided by the screen size, but that makes a problem. Oh, that's how you calculate the scale. So we don't want the scale, we want the screen or pixel size. So it's the scale times the current screen size. So we have to multiply each of these vectors. So okay, let's real quick show. So let's just let vec equals vector 2 : Is there a new? Yes, there is. Let's just do 2.0 2.0, and what can we do? Vec dot multiply. We can other vector 2. We can do an other vector 2. Dot, is there a scale? Scale vector by scalar. Okay, so scale is effectively multiply. We multiply it by the screen. We multiply horizontally by the screen dot width and vertically by the screen dot height. So yeah, we're gonna do that. But I don't think I'm gonna stream it anymore. It sounds bad, but I don't want to. I need deep focus for this. All right, it's been a while since I've done like graphics stuff, so